Joining us here present in Huntsville today is Dr. Douglas Buettner. He is the Deputy Chief Scientist of the Acquisition Innovation Research Center, or AIRC, a multi-university applied research center led by the Stevens Institute of Technology. Buettner has a BS and MS degree in physics and also a Ph.D. from USC in astronautical engineering, with over 30 years of industry experience in the engineering of aerospace and software-intensive systems for the Department of Defense and NASA. Dr. Buettner is also Chief Technologist for Cider.io, an innovative iPhone app for crowdsourcing the observation of UAPs to support their identification. Joined remotely today, Dr. Buettner will also have Nick Snell joining us, a senior studying mechanical engineering at the University of Utah. His goal is to work in the aerospace industry on rocket propulsion systems, and he isn't in the classroom studying rocket science all the time. You may find him enjoying local Utah and the mountains, where he will either be snowboarding, mountain biking, rock climbing, or perhaps spotting UAPs in this ongoing collaborative research effort. So I now welcome to the podium and welcome remotely Dr. Buettner and Mr. Snell.
Thanks, Micah. So I just want to say that everybody here at the end of the conference needs to make sure we give Micah a standing ovation, because quite frankly, I think he's been fantastic. So I want to talk to you a little bit about some research we did, you know, and listening, you know, kind of Nick and myself are going to be kind of your final two before the panels. And some of this is actually going to be some cleanup, right? So we're going to talk about a case that was actually discussed last year, and the fundamental geometry, or the agenda, if you will, is some stuff we did. We presented it at the IAA conference, Space Situational Awareness. And when I say we, I mean Nick did a fabulous job there. He had about 20 minutes to get up and talk specifically about what the students did. But what I'm going to do is I'm going to go through just a quick reminder of the actual MUFON case that was discussed last year, 124-190. Dr. Richard Griffiths, the University of Hawaii. And so what you'll see now this year is that you got two universities now working together on this, actually with the SCU. We had a lot of phenomenal support from Dr. Sarah Little and Richard also. But we'll go through some of that as we're going through the talk. The other thing that I want to talk a little bit about is, you know, after I go through the astrometry that Dr. Griffiths did, we'll talk about a little bit of the quick orbital modeling that I did. And after I was able to confirm you know, the fact that it was probably, I will say, better than 90%, better than 95% likely Starlinks, we were able to get much better data working with one of the online companies called Celestrak that actually maintains all this data. So you can go in what I call proactive mode and reactive mode, pull the data. But what I wanted to do is, because I'm a former Aerospace Corporation employee, I've actually got software that Aerospace maintains for the government. As an aerospace employee, you can have it, and I was actually utilizing it for some of my work. But I wanted to make sure that the methods were available for everybody else too, because they don't have the specific software that I had. And so Nick will talk a little bit about that. After Nick's discussing what I had them do in one of my space mission engineering class, we'll talk a little bit about the geometry. I'll get to show you some equations, which, you know, us physicists love to do. But then we'll go through just a little bit of discussion and conclusions. Okay, so the case itself was a MUFON case 124-190. Like I said, you know, this is actually a very compelling case for doing a case study. Why? Because you had multiple witnesses. They were basically on two different aircraft over the Pacific at the time. You had three pilots on one flight. One of the pilots was in training, and on the other flight you had two pilots. Those two flights were AC-536 out of Maui, Hawaii, going to Vancouver, British Columbia, and the other one was AC-34 going from Sydney, Australia to Vancouver. And so they weren't that far you know, apart in the sky at the night. And then specifically though, one of the pilots on AC-536 took out their iPhone 12 grabbed one photograph, took a short movie, 16 seconds, and then took another photograph. So I had actually 2 photographs that I could analyze. And specifically, when I say I mean we, because Richard Griffiths did a lot of the work here and just did a phenomenal job analyzing it. But one of the things you'll see with scientists is we tend to get very stovepiped, okay? And one of the things you see with it now, you got a 2-university collaboration, which one of the things that I would actually point out with the SCU is striving towards getting those multi experience groups together, your biologists, your physicists, your rocket scientists like myself, and others to take a look at this problem, right? You bring a lot of people with different experiences together, and what you're going to start seeing is the results from that approach. And then we'll also show really quick, like say, one of the frames from that 16-second movie. Okay, so these are the 2 images, okay? On the left side, you've got the one that was taken, photo 1 at UTC 11/39/08, the year 2022, 08, 10. So UTC is coordinated universal time. Then the video happened, and then the second video, or the second image on the right, is more of a zoomed in image. You can see that the image has been rotated. Dr. Griffiths told me apparently the pilot had taken a photo and then took the movie and then had to rotate the camera for the second image there. And so what you see is this object, and I wish I could show the laser, and you see it on the screen back, as you're watching the presentation. But obviously that elongated object there did not look like a standard Starlink, right? And I know Mick West was the one that actually pointed this out afterwards, that it was most likely Starlinks. And I want to zoom in on this one right here. You can see how actually close it had gotten to Castor. Specifically, the constellation here is in it's Gemini, and I love the little thing next to my -4 mag. That's supposed to be a tilde, approximately -4 mag. But fundamentally, it was about 5.5 times brighter. The software that Dr. Griffiths used was SAO Image DS9. It's out of Harvard. It's astronomy software. Fundamentally, he used that software to break out the RGB components from the image. And he can correct me if I'm wrong, but I believe I remember him saying they were about the same magnitudes. And then one of the other things he did is use that to come up with the approximate magnitude of the actual object. And let's go to the next slide here. Now, if you actually zoom in on the object itself, he's got about a 1.5 degree estimation in terms of the size of it in the image. And if you try to assume a distance, which the pilots did, and those are nautical miles, those aren't statute miles. But if you assume a 30-mile distance, that thing would have been about almost a mile long, 0.8 miles. And if it was at 20 miles distance, it would have been about half a mile in length. Okay, now we're going to go and show you the specific image from one image from the movie. And this one is a little easier to see what we'll call a gap or a band structure in the actual image itself, which kind of leads you to believe that the photographs were potentially overexposed a little bit, right? Because in the movie you can see definitely there's something there. And based on some of Dr. Griffiths' discussions on this, they talk about potential orbs associated with it and everything else. I mean, I would say the optical of what you're seeing versus what you can grab by the photographs, that this would maybe potentially describe some of those witness reports. Okay, so one of the things we needed to do, obviously, was understand where the aircraft was when the actual image was taken. So the data itself, when I got involved, was actually from Flight Radar 24 from Dr. Sarah Little. She provided it, but you can go pull it yourself. You can go For example, a flight aware, if it's within a year, you can just get a free account and pull it down. So what I did is I provided some information where you can do that yourself. Part of the reason I want to do this is I want to teach you how to fish, right? I don't want to do your fishing for you. This takes a lot of time, and I don't want to be the only one doing this. I want everybody able to do this on their own. So here's the kind of the, go in, you can search for Air Canada 536. You can go back and find flights going back years. And I'm going to give you some information in terms of the specific data that we pulled. I've got all of my stuff out on a GitHub site. I should have a slide in here that shows you where that is. But what you see here is the actual radar or Flight Radar 24 data that was provided to us. And one of the things I'm pointing out on this specific slide is the fact that the time is in UTC, okay, Coordinated Universal Time. What you should be doing is trying to utilize UTC when you're doing your analysis, and then you just note where the actual specific sighting was in terms of local time zone. But for calculations, UTC is much better. And then going here, if you actually scroll down in the spreadsheet itself, one of the things you'll notice is that I've got in my data highlighted location in there at, starting at XL row 137, and this is from my analysis. I was trying to narrow down how much data I had to pull into the software I was using, and so specifically this is my pointing out where I started pulling the ADS-B data into my software. And the other thing I want to do is show you specifically the KMZ or the location within Google Earth. So inside of Google Earth Pro, and so Dr. Little had again provided us this data when we were doing the initial independent analysis and confirmation. And so I had this. I was able to then go off and see about where it was, a geolocation. Maybe you can barely see those blue icons, but Rich?
We have a technical issue.
Uh-oh.
Just to let you know, your slides are encrypted, and they can't be broadcast on Zoom because Zoom stops the encryption.
Oh, you got to be kidding me.
So nobody is seeing your slides, which is a shame. Is there any way you know how to take the encryption off of your slides?
I'm surprised they're encrypted because what I did is I provided you on Google Drive. Maybe when they were downloaded, they got encrypted. They
But
should.
these are the ones that I passed off to them,
Yeah.
and so I didn't encrypt them.
Interesting.
So there's an interesting situation that you have no slides being
Well,
shown.
let's do it so the people here can see them, but the people online can.
Correct. We're actually recording your slides, so they will be able to see them at a later time.
Okay, so you're just going to have to trust me, but I'll tell you what. Later today, I will go and I will put them on my Dr. Doug B. GitHub site.
Good.
Okay, and
Thank
so
you.
I'll put them out there so then you can take a look through them. And my email is easy to find
All right.
at the University of Utah. So we'll just make sure we get all that to everybody so that they can take a look at it
Thank you. I'm
afterwards.
sorry for the.
Oh, no worries. I'm like looking. What's Rich standing there for? All right, for everybody here that can see stuff, the blue icons, blue star icons coming up from the bottom is obviously your Sydney, Australia site or Sydney, Australia flight, and the ones that are kind of a goldish star, that's your flight out of Hawaii. Okay, so going to the next slide, I want to zoom in now on where the actual photos were from. And so you kind of see that little photo icon right there in the middle of that KMZ file. And so that's the location of the two photos. With 16 seconds, you're not going to get too much of a difference in the ADS-B data at this zoom in factor. Okay, now I want to talk a little bit about orbit modeling. And so, going off and getting my Ph.D. in astronautical engineering, how to do orbital mechanics is one of those things that they really would like you to know. And so I took a class in this, and obviously there's actually this could be a full year course. And in fact, at USC, it is a full year course. You can take 2 semesters. I would say I've taken 1 semester. Am I an expert in orbital mechanics? Not even close. but I know enough to be dangerous. So that's why I've offered my services to help do this. Not only did I know where to pull the data from, but the first thing I obviously need to do is understand, well, which Starlink group are we talking about? And so what I did is I went off and specifically I like using Space Launch Now, but there's NASA Spaceflight. There are others out there where you can actually go take a look at when Starlinks are going to go up. It's got the launch schedule. If you're what I call proactive mode, right? And if you're in reactive mode where you're actually having to do like I was doing here, I want to go look at a launch that was earlier. So specifically on Space Launch Now, I can go hit previous launches. And what you see is there's this Falcon 9 Block 5 that went up out of Kennedy Space Center, Starlink Group G426. Yes?
We are broadcasting the slides from here with a camera.
There you go.
Now people out there can see.
They're sort of caught up. Okay. Great. That's good news. So the other news on this one, obviously, is I want you to pay attention to the time zone there. So this was given to us from Space Launch Now in MDT. Why is it showing up in MDT? Well, because I live in Utah, and I pulled it up in a mountain time zone, so that's what's telling me when it was launched, according to my local time when I accessed this website. So again, you'll need to make sure you put it into UTC time zone. So what is a TLE? So now I'm going to tell you a little bit about what you need to be able to do the modeling with. And a TLE is affectionately known as a two-line element. And the two-line element part is the bottom part of that. The overall thing I'm showing you here is called a 3LE, or a three-line element. And the three-line element, the very first line, is the name of the thing according to the satellite provider or the rocket company, like ULA and others, SpaceX, what have you. And there's going to be information I'm going to provide you here in a second, as soon as I get a drink. That will help you understand how to actually read these things. So the actual TLE format is from NORAD. It's I would say an almost antiquated format. The reason I say that is because of the satellite identifiers in this. They assumed a certain format back in the 60s when they started doing this stuff, and we're just about out of the ability to utilize this format. And one of the things that I'll show you here in a second. I wish, again, my laser pointer, well, if they can see this, I wonder if they can see this. No, they're not seeing that. Is the actual, I'll say, designator for the satellite. The actual first line there, I've got a backup slide in the slides that I'll post later. But if you really want to see, you can go to this website, the Wikipedia. It's got a wonderful description, and all this is fundamentally out of the Wikipedia website. It's all correct. You don't need to worry too much about that. This part right here down on the second line is the orbital elements, also called Keplerian elements, from one Johannes Kepler. And specifically what you can do with this stuff is it's equivalent to a state vector. Physicists know what a state vector is. State vector is basically your position and velocity information about an object, okay? Somewhere in space. It's got a location, and then it's got some kind of velocity aspect. And if you want to show the actual orbital information about it, this is kind of what it looks like. Nick may recognize that specific graph on the right from class, but some of the equations I've got in there, I tried to document on this graph everything that you need to know. So for example, the field 4, right, essentially the ascending node, that's that capital omega there. And fundamentally, it's the angle from the vernal equinox to the ascending node. And the ascending node is where the satellite is coming up above the equator and going up, north. And then the descending node, obviously, is on the other side, 180 degrees around the Earth, to where it's actually starting to go below or down into the southern part of the Earth's, let's say, latitude, longitude coordinates. And so the other information there, you can actually use this once you know all 6 elements. you can actually go through and do predictions in terms of where the satellite's going to be. Okay, let's go to the next slide. So Starlink Group 4026. So one of the things we did was worked very closely with Dr. Kelso, T.S. Kelso at Celeste Track. He's an old Air Force Academy grad. He maintains this website with NORAD. He pulls NORAD data into it. And he also works with SpaceX. And so SpaceX actually provides him data in advance, if as soon as they can, for the predictive aspects of a launch. So that's why I like using this one. There's also spacetrack.org. I've used it for some stuff. One of the things working with Dr. Kelso, he's actually modified his queries and his website to help us do this better. Just phenomenal in terms of working with him. And so I'll give you an example of how to pull these things, but there's other ways to pull it too. So one of the things you want to do is you want to go find, this part of the website. When you go there, there's this search cat, SatCat. You're going to select it, and then it's going to pull up this kind of a window. And if you actually go to the website, you can scroll down and you can see there's other ways to pull stuff too. For example, you can pull a CSV file, and then you can search through the CSV file for a specific launch time, and then go again back in time. But the other thing you want to do is up here on the right-hand side, near the top of that window on the right, you'll see a special data request, SUPGP. SUPGP. Make sure you understand my pronunciation. The thing that is important with that is that's what you're actually going to use to request the TLEs. And so specifically, one of the things you're going to do, if you have gone to the CSV file, you'll find specific information on a specific Starlink launch, for example. And if this is prior to launch, this is what the data is going to look like. And you're taking that and you're going to decompose it into the full year. And then the actual, that 097 is that launch number for that specific year, and that's international designator. The reason I'm showing you this approach is because the old approach is going to probably become OBE, as we need to start using the international designators because we're getting so many launches and stuff. SpaceX is basically overwhelming the system, if you will. But then what you're going to do when you actually go to the supplemental GP, and you're going to put in additional information. So in the backup charts I've got like I said, I'll post it out on GitHub for you. When you go into those charts, what you'll see is the actual steps, and I might even rearrange them so it's more sequential. But just to make sure we get through the full talk here, I want to just kind of shorten it up a little bit. But you're going to get data files for each one of these Starlinks, and it's going to look something like this. You're going to have a Starlink 4522, same exact number, but then you'll see that the actual what's called a time and date designator, which basically is a fraction of the year. So it's got so you see the 22 up front on that the first line of the TLE. The fourth element in has got the last two numbers of the year, and then after that it's the day number of the year, and then after that it's the fraction of the day. So I'll give you a little bit more information on how you pull that. There we go. And so the other thing you want to do is identify the time that is closest to the photographs, or whatever it was that you saw. I want to see if it was potentially Starlinks, right? And so you can go find the launch that's closest to when you saw it. If there wasn't one, it could be further out. Most likely it's not going to be specifically a Starlink group that's transitioning up to its final orbit. So one of the things, you go out on our website, you'll see this Starlink 810 TLE. That's the actual one that we've got, that we utilized for the paper that we published that's out on archive. Okay, so this photo UTC in that, it's actually called AC536XLSX file that's on our GitHub site. If you go to the right there, you'll see this photo UTCs. Literally what I'm doing there is I'm converting that the UTC time from the photograph into a TLE equivalent day fraction. And that's how I'm doing that comparison, right? So I'm trying to find the closest time for each one of the satellites. There were 52 of them in this specific launch. And so I'm looking for 52 times by hand right now. You can automate it later with Python or something, but trying to get as close to that day fraction as I can. Okay, so SOAP. SOAP is Aerospace Corporation's Satellite Orbital Analysis Program. If you look at the specific dates here on the thing, the copyrights, you can see we've been building it since the 80s. 89 is the first copyright. And so as a former Aerospace Corporation employee, again, I've got this. They know I've got it, and then they said they're not going to send the software police after me. So good, I can still use it. But it's very helpful for this kind of stuff, right? And it runs on a laptop. So I use a lot for doing quick checks on things anymore. But I just kind of want to provide this just to show you that my name is in fact on the registration here. But when you start it up, this is kind of what you see. And this is the window here where I'm actually going through and searching for the specific TLE file. I can just upload it, which is fabulous. And you should be able to, if you put all of your TLEs in one file in the 3LE format, you should be able to pull them all into most software. So importing the ADS-B data, however, is not as easy. There's actually a couple of ways of doing it. What I did is for the quick check, I decided to go ahead and just manually insert it in. Nick will talk a little bit about that, I'll say dilemma as well when he talks. But one of the things here you see me pulling out is this mean sea level problem. And so the software itself, when you have satellites up, it needs to take into account the gravitational model of the Earth. And so the software, you go to where I'm going to put the AC536 route in here. You can see the mean sea level is there, right? But then I've got terrain at waypoints. So they've got different capabilities. They actually have also the ability to pull in a KML file. So you could, if you wanted to pull, for example, CSV data into Geo or Google Earth or some other platform like that, export a KML file, and then you could potentially pull it into Aerospace's or even potentially SDKs, but we'll talk about that in a little bit. So one of the things I need to do is actually go through and figure out, okay, I've got to convert this, right? And so that's Dr. Little and I worked with back and forth a little bit on how to do this. In the paper that's on the archive, I talk about a website you can go to actually do this translation. And so what you see on this specific screen is you see the actual raw data on the left, right, that AC536, and it's got the, let's say, the timestamp, the UTC time. It's got the flight number. It's got the location in terms of latitude, longitude. It's got the altitudes in barometric feet, okay? So we have to convert that. The next column, you see me converted it into kilometers. And then after that, it's a couple of things in terms of speed. And then the last column there, that I column, is the actual direction of the space or of the aircraft. So I'm going to go back for a second here. The next tab over, that's the converted geoid height. And then you're going to see an AC536 tab in there as well. Now let's go to the next one. So this is kind of what gravity model of the Earth. And so you got a mean sea level. And so if you go Google this online, what you'll see is that capital H and little h go into a point on the Earth. Well, I'm not talking about something sitting on the planet. I'm usually talking about a satellite, or in most cases, or specifically this case here, we're talking about an airplane, right? But the capital H is the distance that you want from the mean sea level, or geoid is another word we use, up to whatever platform that is. And it's actually going to vary in terms of how far it is from the Earth based on the gravity, specifically for satellites. And so I want to do that same thing for the aircraft inside of SOAP, because SOAP is an orbital analysis platform. And so I had to do this conversion. Again, in the paper we talk about how you do this. And so basically now if you go over to this A536 tab, what you're going to see is this specific layout. And one of the other problems you have with barometric altitude is you can potentially have an error in that altitude. up to about 2,500 feet, depending on whatever altitude the aircraft is in and various other situations. So what we did was actually in the paper we talked about a potential up to 1 kilometer. It's actually 0.8 kilometers error that I put in just to see if it would affect the actual location of the satellites as viewed from the aircraft. Because I'm trying to model it, right? I'm trying to replicate what the pilot saw. And so that's why you got that in there. That blue line right there, the row 142, that specifically is the time closest to the actual photos. So, all right, photo 1. So I've got everything in here. What does it look like? That's what it looks like. So inside photo 1, you got my aircraft. You know, I've got lots of view capabilities within SOAP, but specifically at the photo 1 UTC time, again, pulling the TLEs, I take SOAP and I tell it, okay, show me 11:39:08 UTC on 2022, August 10th, and that's where you see the satellites. I'll zoom in on this a little bit better. I did this in the paper, and what you see is that, okay? Photo 1. Now let's show you photo 2. Photo 2, again, now I'm going to go to the second time here, and you see it's almost sitting right on top of Castor in Gemini. Again, zoom in on it a little bit. Okay, I'm going to take that, I'm going to do there. Now in the actual paper itself, I was able to, and trust me, this is not easy, I wish it was easier, be able to, from the view of the aircraft, try and zoom in even closer, right? So you can actually see the spacing of the actual satellites themselves. It took me probably 10 minutes of fiddling within SOAP, because I can't just type in a coordinate and say, hey, move my camera to such and such a location or my viewpoint. But if it did, it would be a lot easier. But after the 10 minutes, playing with this, after we had the right TLEs in there, you see that. And so one of the things, if you look closely, you can kind of see it's at a slightly different angle. And that's an artifact of my trying to zoom in on that specific view of the satellites. But one of the things you notice in there is that gap structure. So I am telling you the best information we have in terms of where those satellites were actually situated as they deployed from the SpaceX rocket at that time, okay? So, you know, me being a scientist, I'm going to say that's probably better than 90% smoking gun, that this is what we saw last year, okay? All right, now the student project and orbit and rendering. So hopefully Nick is ready to go, and we want to turn it over to him. But specifically, he'll talk about what the students were doing in the space mission engineering class. So we can flip it over to Nick. Yes, we'll need his PowerPoint, and we will need him. And there he is. Hey, Nick.
How's it going?
So you ready to rock and roll? All right.
So, yeah.
All right, we got your slides up. So go ahead. I don't know if you can see him, but we can see him here.
All right. Hi, all. As you know, my name is Nick Snell, and I'm a student at the University of Utah. And I will specifically be going over the modeling done by myself, a fellow student, John Stilley, and Dr. Buettner for a space mission engineering course also at the University of Utah. So, since SOAP is only available to aerospace employees and their government customers, Dr. Buettner wanted the modeling redone using publicly available tools. He offered the following project to his students in his space mission engineering course at the University of Utah. The first task was to model the launch and the Starlink locations using ANSYS/AGI's Systems Toolkit, or STK, after identifying other potential modeling tools. And then the second task was to identify tools for and do physics-based visualization or rendering, provide a photorealistic cockpit view of what the pilot saw that night. OpenSpace, which is a professional rendering software, was recommended to us. However, we chose not to use it due to its overall complexity. So, First task was to model this in SDK. As Dr. Buettner already went over, the necessary modeling info is required. First, you need AC-536's ADS-B flight data, which was found on flightaware.com. Second, you need SpaceX/Starlink launch information, which was found on Space Launch Now. Also, you need SpaceX debris and Starlink satellite TLE information, which we found on Celestrak. And then lastly, Falcon 9 launch information, which was found on SpaceX. However, that's only needed to add fidelity to the overall model. It's not required to do the complete model, I guess I should say. So, right when you open SDK, the dialog box to the right will open. First, you select Create Scenario, which then opens the dialog box shown to the left, or the SDK New Scenario Wizard. The required information to recreate our scenario is shown in the box. Most importantly, you want to change the start time to be a couple hours before when the actual SpaceX launch took place. So in our situation, I chose August 9th, 2022 at 6 p.m. UTC time. So your first step is to model the aircraft flight path within SDK. To do that, we selected Insert, which is an option in the top hotbar of SDK. After clicking Insert, we selected Aircraft and then Define Properties. Once we selected that, the dialog box to the right opened up, or the Aircraft Basic Route window. In this window, we made sure that propagator was selected as Great Arc. After that, you need to change the start time to be the UTC time of your first available ADS-B point. After that, we selected click Insert Point, which can be seen on the right side of this pop-up window. Once you select Insert Point, a point will appear in the dialog box. In that, you want to change the latitude, longitude, and altitude columns. I know it says speed columns, but that's a mistake. SDK will automatically propagate and update that speed column as you add more points in. After adding in your first point, you just want to repeat until all the ADS-B points have been entered into the window. So, if done correctly, your aircraft pop-up window and SDK 3D viewer should look like the following. To the left shows the aircraft basic route window with all of the ADS-B points inserted. And then the image to the right shows the 3D viewer within SDK, where the blue line represents the flight path of AC-536. So after inserting the aircraft, you want to add in your Starlinks. So using the TLEs we obtained from Celestrak, we had to add them into the SDK scenario. So again, we selected Insert, then Satellite, and from a TLE file, which can be seen in the left window there with From TLE file highlighted in blue. After selecting Inserted, we were prompted to select a TLE file from the computer. The location of that file is all dependent upon where you ended up saving it. After selecting that TLE file, the pop-up window to the right opened up, which is just prompting us to select which satellites we wanted to enter into our scenario. For us, we wanted all 52 Starlinks, so we selected all of them and then clicked Insert. After clicking Insert, going back to your 2D and 3D windows, it should look like this if everything is done correctly, where the purple line on the 3D viewer represents the orbit track, and then to the right shows the 2D viewer, which just shows the ground track of all 52 Starlink satellites. So the results of SDK are shown below. After zooming to the aircraft, this is what we see, where the blue line now represents the Starlink satellites, and the red line just shows the view path between the aircraft and to the Starlink satellites. The aircraft shown in this image is not what it will actually be within SDK. This is an external model I uploaded into SDK just to match the actual aircraft that the pilots were in. The model shown in the picture is, I believe, documented in our paper, and then it's also available for download in the GitHub if you would like to recreate exactly the image shown here. So our second task was some physics-based visualization. Originally, we were just tasked to identify the pros and cons of some available rendering tools. We initially looked at OpenSpace, Autodesk 3ds Max, and Blender. However, we ultimately selected Blender due to its price. It was free, and the broad user community available online. In addition to our original perception that the physics-based modeling within Blender would be pretty straightforward compared to the other two softwares. So the screenshot to the right just shows what Blender looks like after you start it up, just as an orientation to you guys. So the following steps will be needed to create the actual model. You will need to add an aircraft model, a model of the Earth, add some lighting, and then lastly, add the Starlinks in. So to add the aircraft model into SDK, we used a free model that we found online. Our paper documents which one, and I believe that file is also available in the GitHub. However, Blender will not accept all CAD files, so depending on which one you choose, you might have to convert into a file type that Blender will accept. Then we imported the model into Blender. This was set at the center of the scene. This makes the orientation and adding of additional elements such as the Starlink or an Earth model much simpler. Then after adding it in, we had to scale the plane to the correct size. All of the units within Blender are in kilometers. So for example, a Boeing 737 is 30 meters long. I'm not going to do that conversion in my head because I'll probably mess it up, but you get the gist. After that, we added in a spherical representation of the Earth using a UV sphere. After adding that in the Items tab, we changed the dimensions of the UV sphere to be 12,742 kilometers, and the Z location to be minus 6,371 kilometers, plus the aircraft's altitude. After that, we right-clicked on the sphere and selected the shade to be smooth. And then in order to get the sphere to look like the Earth, we had to add in some Earth satellite imagery. So in the shading tab, create a new node, and then attach an image texture node with the image or the satellite imagery of Earth of your choice. Lastly, we changed the background color to be black to represent the night sky, and then we rotated the Earth to approximately align with the position and heading of the aircraft. Next, we added in our representations of the Starlink satellites, which ended up being Blender cubes. We modified the dimensions such that they were as tall as the aircraft is long and as wide as the aircraft's fuselage. The exact scale was hard to achieve, which is why we ended up using those dimensions as our size. Next, we changed the surface material properties of the cube. We used an emission to simulate the rectangle reflecting the light. The surface was glass using a bidirectional scattering distribution function, or BSDF. And then after changing the surface properties, we had to make these satellites move to their actual location within the night sky. So using azimuth, elevation, and range data, or AER data, which was initially obtained from SDK, we converted that into X, Y, and Z coordinates. And then if the reflection angle is calculated, that can also be added here. However, that is not super necessary for it just adds fidelity to the final model. And then after making the first Blender cube, you will need to copy and paste new rectangles to represent all 52 of the Starlink satellites. And then all you have to do is just change their relative location to be each of the AER coordinate data points found from SDK that relates to each individual Starlink satellite. So then after adding in the aircraft, Earth, and the Starlink satellites, you will need to add the sun object. So we added in a sun object, and we found that the size didn't affect luminosity. So if you wanted to, you could make it as small as a grain of sand. or gigantic, just as long as it didn't clip with the overall model that you've created. Next, we needed to position the sun accurately to represent where it was at the time of the photographs. So we needed to attach a new sun object to sun position in world properties. You may need to enable sun position in your preferences tab first. Then we adjusted the date, time, and north offset to be the time of the first photograph and model airplane heading. We set the distance to be very far away so that the sun didn't clip with our model. And then we set the strength properties in the data properties tab. We also added in a small amount of light in the cockpit of the aircraft just so that the outline of the windows were visible, just to orientate the viewer where they were sitting in the Blender model. So what were some of the results we found? Initially, we had to move the distances of the satellites to be much closer to ensure that we could actually see them after rendering. However, after the term was over, Dr. Buettner modified our models to run some experiments. First, he moved the satellites out to their correct relative distances from AC 536. And second, he wanted to see if they were visible with or without their solar arrays deployed. The two pictures shown below are screenshots of Blender before the rendering was done. The left picture shows the Starlink satellites without their solar arrays deployed, where the right picture shows the Starlinks with their satellites deployed. And then after running lots of experiments, some of the results Dr. Buettner found are provided on the next few slides. So again, this is a screenshot from your from our Blender window before any rendering was actually done. The small orange dot, I don't know if you guys can see that very well, but the small orange dot with the yellow arrow pointing to it is just the position of the Starlinks within the Blender model. It's not actually how the Starlinks showed up in the final model. And then this next page, or this next picture, is an actual rendering of our Blender model, specifically with the solar arrays not deployed. As you can see here, the Starlinks are not visible from the cockpit of the aircraft, specifically when their solar arrays are not deployed. And then this next picture, as the caption says, is with the solar arrays deployed. The very pixelated object is our rendered Starlink satellites in the Blender model. I believe this picture shows that we are on the right track in terms of proving that what the pilot saw was Starlink satellites. And what I mean by that is that it has the relative angle, or the same relative position in the sky and also same orientation in the sky. However, due to some of Blender's limitations, we aren't exactly able to get an approximate brightness to compare to what Dr. Griffiths got from the original photograph. So what were some of the challenges that we ran into and that you might run into creating these scenarios yourself? Most importantly, inserting the ADS-B data into SDK was quite difficult. As you can imagine, inserting each of the hundreds of ADS-B points into SDK individually can be quite cumbersome and boring. If you do end up recreating this, what I found works pretty well is just taking the two ADS-B points that bracket the photograph that you want to recreate, and then just inserting those 2 points into SDK. Second, SDK was unable to model the Starlink deployment from the Falcon 9, or at least as near as we could tell. Doing some research, we deduced that SpaceX will tumble their upper stage before they release the Starlink satellites in order to get adequate separation between them after they release. Thirdly, Blender's fidelity with the satellites at their correct distances did not allow us to replicate the photos. And also, no accurate Starlink CAD models were available to use online, which is why we ended up having to use the Blender Cube to represent the Starlinks. Lastly, SpaceX also doesn't provide much information about their Starlink deployments. That can be expected. It's probably proprietary, and they don't want people recreating what they're doing. However, some of the questions we had were how are the satellites released from the second stage? When did the solar arrays deploy? When did the ion engines fire? We think that SpaceX transparency could be improved to help make modeling this problem a lot easier.
Okay, so that's the completion of Nick. So if we can go back to my slides. Okay, so I just had a request from Micah. Excellent. So now that people online can see this, I'm hoping they can see it now. If somebody could send a message up to Micah, whether or not. But I'm going to go backwards and show you those original photos. So if you'll bear with me for a second. Okay, so I had, again, the discussion of the actual MUFON case. So these were the two photographs, just for everybody online to just kind of remember from last year and those that weren't on last year. So you see the line there is what the pilot saw. I mean, if I was a pilot seeing that, I'd go, what the hell is that, right? So what you see is in the first photograph, it's at the 3908, and then the second photograph at 3924 UTC. It's a lot closer to Castor. And then going in and zooming on, you can see how close that is actually to Castor. And then the next one, we kind of zoomed in and kind of saw from the work that Dr. Griffiths did in terms of what the angular size of that object was. And the next photograph here shows that gap structure. And so now you can see how close our modeling was able to get that gap structure in terms of location. However, obviously I was going after the physics-based modeling as well. So now we'll go through all this, and again, I'm going to defer to you to the online stuff that I've got, and I'll repost these out on my GitHub site. All right, let's get down here. Teles. So. Almost there. Okay, so now to current time. All right, now I'm going to go through and provide you some equations. I'm sorry for the non-mathematically inclined in here, but this is what we do. State vectors. So a state vector from the aircraft coordinate location. It's something we wanted to do because that's where our photos are from. That's where the movie's from. And so what I'm trying to do is kind of replicate what I saw in the geometry based on knowing that these were in fact Starlinks, right? So I'm trying to do, or what I'll be showing you is fundamentally a coordinate transformation from what's called ECEF coordinates, or centered Earth fixed coordinates, which is what the modeling software will provide. It can provide other coordinate systems, but that's probably your best. And what it's doing is it's actually fixing the location of the satellite in orbit with respect to the center of the Earth. And that RIN, that's the position vector from the aircraft to the nearest satellite, and to the right is the position vector to the furthest satellite. And if you do a projection down along the RI equals N to RI equals F onto that F vector, that represents the actual distance from the aircraft to the perceived actual distance of that satellite train, because it's at an angle. And so if you can see my pointer here, right? And so if I show you something like this, what you're seeing is the length. But if I show you something like that, that's not what you're perceiving. You're not perceiving the actual length, right? You're perceiving an angle representation, okay, along that, flat plane. Oops. Along that flat plane to what is actually visible. It's a problem of geometry, right? Three-dimensional geometry. So what we're trying to do now is actually take and, let's say, represent it now, and actually go through and decompose it and trying to reproduce what we saw in the photographs. So quick quiz. Anybody know the answer to this? Gosh, I'm embarrassed. This is supposed to be the SCU. You take the dot products between the two vectors, people. Okay? That gives you the cosine of the angle. Come on. It was your first guess, right? Oh, and then there's this minor detail. You've got to, take it by and divide by the square root of the actual distance, right? That's the RN and RF. And then, oh yeah, you got to multiply by 180 and divide by pi, and then the arc cosine. So that's how you do it. Okay, everybody knew that, right? All right. So using state vectors relative to the aircraft. So first thing you need to do is actually put them in the ECF. So I've got from position of the Earth. So actually just doing the subtraction. That's all you have to do. And so now they're relative to the aircraft, but again, they're still in ECF. But geez, I want to actually do some other stuff. But before I do that, first I want to show you the geometry. Okay, so you actually go into the Python that I posted online too. What you'll see is me actually doing the coordinate transformation to a satellite. So I actually go do ECF. So I've got the position of the aircraft, the position of the sun with respect to a satellite. And in so doing, what I'm trying to do is come up with that glint angle. All right, I'm trying to understand, based on the geometry, if the sun is over here and I'm a satellite and the aircraft's over there, what's that angle? And so this is how you calculate this. This is my not knowing exactly what the orientation of that Starlink satellite is. So I am assuming that it is at a specific orientation. And you'll see that's one of the things I beat up on them a little bit in my paper, is that we don't have a model from SpaceX in terms of what the orientation of these satellites are in orbit. And so we have to make some assumptions. But one of the things I want to point out here is this absolutely wonderful paper from Fankhauser et al. Titled Satellite Optical Brightness. You can Google it, find it online. Obviously, I referenced it in our paper. But it's the basic geometry of what's going on. Now, one criticism I found online, I will leave out of the discussion and where I found it, was the fact that we didn't discuss satellite flares. Why didn't we discuss satellite flares? Same basic geometry, but I don't have any photographic evidence. We do have some witness testimony that they saw flares, and there might have been some flaring going on, but I don't have a photograph that I can go off and do that. One of the things that was really interesting, obviously, with this one is it persisted for so long in terms of how long you saw it. A satellite flare will just be a few seconds, and we'll discuss that here in a second, but I want to give you some more equations first. All right, Earth center fixed. I need to rotate that. In this specific case, what I'm doing is for the AC-536 aircraft, right? If I had selected Starlink, I would be doing this rotation with respect to the latitude and longitude of the satellite. And so what I'm trying to now do is put everything in perspective in terms of where things are with respect to my airplane sitting up there. Okay. So after you do that simple rotation, everybody knows how to do that, right? Now we're going to go through and specifically tell you how I'm going to actually plot it, because I want to be able to say these are my look angles, from the specific aspect of my pilots in terms of what their heading was. And one of the things I wanted to do was have positive angles to the right from the nose, and I wanted to have negative angles to the left. And so that way, inside of the software there, inside of Blender, for example, it's very easy for me to make sure that I've got the right location. So one of the things we have to do now is actually you do the coordinate transformation, but to make sure you've got that specific positive negative, you actually have to feed it a negative angle. And what happens is your cosine is a positive function, and you feed it a negative angle, it's going to be still positive. But a sine, however, is a function to where if I feed it a negative angle, it will flip sign. And so what happens is you see your signs changing sign. Okay, say that 10 times fast. Now I'm going to actually calculate for you the alpha look, the look angle, and then the elevation angle. So that's going to be your elevation up or your elevation down, again, positive or negative. And so this is the specific equations for that. And now I'm going to show you me pulling all the data into Excel and plotting it. And again, all this stuff is online. In my GitHub site, you can actually go look at those specific graphs. I am showing you where those satellites were with respect to Castor for photo 1. And then what you see on the little add-in there, you've got the actual degrees, the maximum look, minimum look angle. So I'm actually doing calculations based on where they're showing up. And now photo 2, again, what I did for each one of these satellites is inside of SOAP, I literally extracted Earth-centered, Earth-fixed coordinates from it into an ASCII file. I've got Python scripts that then go through that, pump it into something that I can now pull into Excel and start plotting. And so that's where it was in terms of the second photograph. So how close were we? So the first one here, apparent length, from a geometric model, I was at 1.1 degrees. And from astronomy, or astrometry.net, and the actual wonderful analysis that Dr. Riffs did, about 1.5 degrees. Apparent speed is the actual distance it traveled in degrees per second between the first photograph and the second photograph. And you'll see from, again, the work that Dr. Riffs did, he came up with about 0.26 degrees per second, and I came up with about 0.23 degrees per second. Now, the apparent magnitude, he came up with about -4, and I'm saying incomplete. Why am I saying incomplete? I am not happy at all with the rendering that we did within Blender. I think we can do a better job. I'd like to go back and try and do this with OpenSpace, which is some software that actually University of Utah and others around the world are working on with NASA to actually provide, let's say, very high fidelity software, and that you know, is used for various things, but we think it'll be a much better one. This specific discrepancy, about 0.4 of a degree, we believe is due to a bunch of factors. The relative importance of each factor is arguable at this point until we model it. JPEG probably potentially being a significant one. Atmospheric scattering effects, as well as the fact that the photos were taken from inside a cockpit, right? So there may be some distortions from the actual cockpit window. We didn't model these, and we believe that will account for that 0.4. And potentially the other one. Okay, so here you're seeing an error in my my juggling the stuff around. So again, humans aren't perfect as much as we can try. After three redesigns, only thing that SpaceX has done is literally improved what's called the diffusion or the reflectance scattering. This is a bidirectional reflectance distribution function. It comes directly from SpaceX documentation. If you look at the paper, again, we've got the actual reference in here. But according to them, that first generation of dielectric mirrors at a 60-degree incidence, that spike there at 60 degrees is the specular reflection, okay? Everybody knows the specular versus diffuse, right? So if I take a laser beam and I point it at a mirror at an angle, what you'll see is the angle at the laser is from the beam. You'll see, like, on the opposite wall, the angle, like I showed you in the specific thing, that will be exactly the same on the side if you go off and measure it against the wall. And so I'm not seeing any improvement there. So I'm going to tell you right now, I have a lot of skepticism that we're going to see an improvement in the UAP, I would say, misclassification of Starlinks anytime soon. SpaceX implements reorientations. One individual that contacted me after we got the paper out there, an individual by the name of Tony Miyama, who I reference and thanking him. He's actually gone off and done data. He's been doing this for the astronomy. So, you know, the astronomers know when Starlinks can potentially impact their satellites, or excuse me, the satellites can impact their astronomical photos. That's the right way to say it. But it was kind of interesting because we went back and forth, and so he's now referencing some of our work. And I find it very interesting that SpaceX is willing to work with the astronomy community, but at the moment, I don't see any movement whatsoever in terms of them working with, for example, the FAA, and we'll talk a little bit more about that in a minute. Okay, next slide. There we go. Okay, discussion. What about aviation safety? Now we're there. All right. So what is the FAA doing? There's these things out there called these unmanned aircraft system UAS sightings reports. But I can tell you right now, we've got smoking gun evidence that it does not include all of the potential reports that could be in there. I do know, as you see down here, Congress is trying to help, provide language to protect pilots to report these things, which has been a problem. But this, for example, this UFO over New York City video, I've been working with Ben Hansen on doing that analysis. And one of the things that, when that video first came out, I sent an email off to the FAA asking them for UAS reports from that day. And basically I got a very terse, about 5-word response that nobody knows that. One of the things you find out from Michelle Race, who actually took that video, she contacted the FAA trying to explain that, she had video evidence and no response. Okay, so you have an individual on an aircraft. Why the pilots didn't see it and why they didn't report it is, I don't want to go there. Potentially it's because it's coming up from below their line of sight, maybe. Maybe they just both didn't happen to be looking out the window at exactly the point it was going by. It was going very fast. I estimated about 400 feet per second. So if you think about that balloon would have been traveling faster than a football field per second. Dion can't go that fast. Congress has prepared, like I said, language to protect pilots, but as I read it, there's nothing about having somebody on an airplane also provide information into that database, so that's a problem. How about the Pentagon? Pentagon reportedly is working on multi-wavelength sensors for aircraft, but I don't know, and there's no information that I can find anyway in terms of whether or not that's going to be provided to the FAA, and if there are going to be requirements for a civilian commercial aircraft to also include sensors to help get to the bottom of this. And what about after the paper went out there? They have not contacted me or any of our other authors. Conclusions. So I'll let you decide whether or not we accurately modeled this or not. I'm going to call it, like I said, better than 90% surety. We've also provided in the actual paper itself, I'll say a detailed approach that we believe will help solve some of these misidentifications. And then it will also be available, or it also works for flares, but flares are a slightly different situation, but not too different from the physics. Acknowledgements, there were a lot of people that helped on this. Okay, this is not me, this is not just Nick. The SCU board, want to thank them for the money to get me out here to talk about this specific case. We couldn't have done this analysis without the pilot's photographs, willing to step out on a limb to say, what the heck is this thing? And then we've got a lot of other additional things in here. Dr. Sarah Little was just phenomenal. Professor Griffiths was phenomenal in terms of doing this. And we'd like to thank Mick West for actually pointing this out to us, that it's not, in fact, a UAP, it's Starlink. So, this additional work we did to analyze it is now available to all y'all. So there were also, after we got the paper out there initially, down here at the bottom, we had, I would say, a lot of interest in this. It was very interesting to see Popular Mechanics pick this up. But then after we started getting some initial, I'll say, constructive criticism, we rewrote the paper a little bit. Tony Miyama provided some definite input with Richard Cole in terms of what they're doing for the astronomical community. And then we had some anonymous reviewers who didn't want their names. One was tried to do a hatchet job on this. I worked on all their specific criticisms, and we tried to rewrite the paper. We may actually put another revision out there on GitHub soon. But then finally, Dr. Sarah Little said it the best. To characterize the unknown, we must first develop methods to characterize the known. okay? You've got to be able to split the two out. Once we start getting the data on these things that we specifically can't address, we're better off, and then we'll start coming up with methods to identify those. Micah, thank you.
Incredible lecture right there. I know we're coming right up on lunch. I hope we've got a little time just to work in a few questions here. A couple of quick observations too. You know, you listed all of the people who had participated, you know, skeptics and scientists. I know Mick West has talked about this idea of curated crowdsourcing and being able to work with a huge team of people with diverse backgrounds. This, I couldn't imagine a better example of bringing people across the spectrum together and really providing clear, analytical, information that clearly demonstrates this is what you saw, this is what it was. But now we got to look at the implications too. In fact, my publication, The Debrief, some of you here may know this, we have been very persistent with the FAA about their response to pilot sightings of UAP. My colleague Chrissy Newton and I have actually written a couple of articles, and Ben Hansen has participated in providing information about those. Something that stuck out to me was the point that you made about how there was so little response to this paper from the FAA, so little response to pilots who report these things. What I see in this paper that you've produced and also the lecture that you and Nick just provided is that it seems incumbent upon the FAA to have to recognize the distractions that orbital objects and other objects may represent to pilots. So to you, what do we glean about the safety issues and the responsibility the FAA has with regard to the analysis you've just provided?
Well, it was fun talking to Ben about this because, you know, Ben's take on it has been that, and I'll just say that not all the pilots are on the same page.
Right.
Start there, but Ben definitely had a spin on it, which I found was interesting. He thinks it's a safety issue. If I've got a pilot not, you know, paying it because they're slightly distracted with something outside the cockpit that they can't explain, that's an issue. I mean, how much of a risk it is, I'll leave to the aviation safety community. But, and so there you'd have to do, I'd say, a cost-benefit analysis in terms of, you know, some of the approaches that we took in terms of being able to do this, how much it would cost, what's the actual risk to aviation. So there's methods to go off and do those calculations and figure all that out. I haven't gone there yet, but I'm just saying, here's an approach, right?
Arguably, this is the best framework in terms of how we can better discern, especially orbital objects and the reflectivity with relation to UAP sightings. And again, being able to separate that proverbial wheat from the chaff is very important. But looking ahead also, we had the following question from Matt Phelan here. Let's say we had a ground-based observation of UAP from multiple citizens, raw cell phone videos, metadata. He asks, how might you go about synthesizing that data, like geolocation data in those videos, with the TLE data, or if it could be done, and other satellite data? Your thoughts?
Yes, it can be done.
It can be done. How long might that take?
So as you pointed out, I am also the chief technologist for Cider.io, and that sounds like they've gone and looked at Cider.io's website, and they're trying to ask me if we can do that, and my answer is yes, we probably can.
Would you like to speak a little more about Cider.io?
At the moment, I am going to have to say no. The reason for that is because in working with the inventor, I would say he's just in the process of coming out of you know, what we used to call a silent period of development, right? And so he's being very careful in his rollout, but more to come later.
Here's an interesting question from our audience online. Could this goal of discarding confusion with outer space-related conventional objects be achieved, perhaps also working with certain government agencies, maybe the National Reconnaissance Office or the National Geospatial Intelligence Agency? And if so, can we start a conversation with them about this?
When you start talking those two specific agencies, me coming from the Aerospace Corporation, is yes, you could do that. Will the public know about it? Probably not.
That's the issue again. Yeah, once you start working with the intelligence community, they tend to want to have that information exclusive to intelligence. So the benefit here, of course, obviously, this is mostly what was demonstrated here was with publicly accessible data. In fact, I think in Nick's portion of the analysis, he explicitly used publicly available, often freely available programs like Blender for this modeling. Now, you mentioned again that there were some issues with some of the modeling. You weren't satisfied with that. You also discussed future efforts that might improve on this process. How might we do that?
So let's talk about that. I mean, why was I trying to go to a physics-based model? I don't hear anybody yelling out the answer. Why? Because, to really convince people that you saw something that we know about, you've got to be able to model it and be able to say, okay, you were standing here, you were looking in this direction, this is what you saw. And if I have a physics-based model, then it does a lot more to help convince them that that is in fact what they saw. Now, if they saw some, and I'm getting flooded with, requests to take a look at this and take a look at that.
We're getting flooded outside right now, too.
Yeah, I can hear it. And he means it. It's raining pretty hard here right now. But the issue is trying to come up with, I would say, models, things that we can show the public to say, okay, I can reproduce what you saw. Like I said, after Ben found out I could do this, he went and he's working on some TV show, and he said to me, oh, hey, we've got a sighting. We think it's Starlinks. Can you go model for us? I spend 2 days, get up at 2 a.m. to get the model done for him, and I pull it into STK because I couldn't use Aerospace for that because they want to be able to provide it in a TV show. And I'm literally able to go off and put somebody there. Okay, you're, say, Arizona, looking above this. Okay, you're telling me it's about 7. Well, I can tell you at 7:22 and 37 seconds, you had Starlinks going over you. And, that's the kind of work that we can do with these approaches. But I can't do that for something that's not a space-based object, right? And so that's why I also wanted to start bringing in the physics-based approaches. To be able to, I would say, marry both methods into a more comprehensive method.
Precisely, yes, because with this method, obviously, I would say it's extremely effective and accessible, and maybe not easy per se, but with technical proficiency like yours, you can confidently indicate when we have orbital objects, when we know launches, when we know their positions, and we can track all that. That can very clearly be ruled out. Now, if we can just do that with objects in our atmosphere as well, could be a potential game changer as far as UAP research. I have a technical question, though, here from Mark Elowitz, Ph.D. Does the SOAP software use the EGM 2008 Earth gravity model in its orbital propagator? And also, does the SOAP account for atmospheric drag and solar radiation pressure in its satellite orbit propagation model?
So it has a multitude of different models in SOAP. It's got the 84 WGS model. It's got a lot of different stuff in there. And if said PhD is a government employee, they can definitely reach out to Aerospace Corporation and see what they can do. And I'll just leave it at that.
Excellent. It's about lunchtime. One final question. Are there any other cases right now that you're applying this methodology toward in the furtherance of resolving, what this might have been, what the UAP might have represented?
No, I think people are tired of getting stuff thrown at me and me turning around and telling them it's Starlinks. But I'm not working on anything using this entire thing. I am working on other stuff, like, for example, the balloon over New York City example with Ben, and there potentially will be other things coming down the pipe.
I'll look forward to that. Dr. Doug Buettner and, of course, Nick Snell also joining us remotely today. Excellent lecture, please. A round of applause. It's fantastic work, gentlemen. Thank you again.